Senti, no, io farei l'annuncio, però se non c'è, sono interessato. Eccolo.
Ah, grande.
Non ci parla no.
Ciao Thibaut, ça va?
Ça va, tu l'as vu?
Presque.
Sì.
Est-ce que tu as eu des réponses à la mail que tu as envoyée?
Ah, Cédric?
Ouais.
Non.
Non, mais si, en fait. J'avais pensé t'envoyer un truc pareil, mais je me suis dit, bon.
Oui, non, mais
T'as bien
ça sert à rien, mais.
fait. T'as bien fait, t'as bien fait. Non, mais qui doivent un peu sentir qu'ils ne peuvent pas faire.
Ah oui, oui. Non, et puis je voulais leur dire, écoutez, ok, on a peut-être un peu, mais clairement, il y a des trucs que vous avez pas fait. Au moins pour l'année prochaine, faites-le, quoi.
Ouais. Non, mais surtout, quand même, s'il y a Jean-Baptiste qui est. Donc là, ça va être un truc illégal, non?
Et je pense qu'il a eu raison de le faire.
Il a raison, bien sûr.
Il a fait
Bien
son travail,
sûr.
quoi.
C'est pas Jean-Baptiste qui qui a un faux.
Grazie.
Donc, je cherche un truc pour réinstaller bien la finale.
Je cherche la.
Dopo, ecco la carta.
combien de milliers de vues on a fait sur YouTube avec
Non, mais il faut lancer une campagne de promotion si tu veux. Et là, on peut faire next level quand même.
Bonjour. Et si vous voulez avoir un certificat, il faudrait signer les bordereaux, s'il vous plaît. Est-ce que tu as besoin de...
Non.
Thibaut, c'est la glace quand même.
Des chiffres. Bah, attends, moi je... Attends, je te montre le mien, mais ça c'est le mien avec les calculs que je fais hier. Vraiment toujours. Non, c'était non, pas en direct, hier j'ai relu. J'ai relu. J'ai passé 2 heures à relire. Ah, oups. Okay, so good morning, everyone. Welcome to the second class of the lecture series on the statistical physics of ecosystems. So today, to start, I'd like to finish what we started last time on the Maillard model. So let me just remind you what this model was about. And for the broader context about why we were talking about this model, the idea was to sort of describe in a generic way what kind of dynamical behavior we can expect in systems of interacting populations. And so, I mean, we described fixed points, we discussed specific cycles of chaos very briefly. This one is a bit of a different beast. So these are trajectories that follow heteroclinic cycles. And the fact that these trajectories can emerge quite robustly in an open set of the parameter space is tightly linked to the fact that the equations that we're considering are constrained to live with positive variables, and the fact that the extinction of a species, namely its population size going to zero, is an absorbing state of the dynamics. It's something that we come back time and time again in these lectures. So a bit more specifically, what we're looking at is this. So Ni dot is equal to Ni, 1 minus Ni, minus alpha I n I plus 1 minus beta I n I plus 2 with I equal 1, 2, 3. So it's a free species thing. So these were the conditions. So alpha I is smaller than 1, which is smaller than beta I. And the product of AI is smaller than the product of BI, where AI is equal to 1 minus alpha I, and BI is equal to beta I. Right? This is where we were. So this parameterization, let me remind you, it means that if you're on the phase space, so you have 3 fixed points with only one species, right? So let's say that this is N1, N2, N3. There is also an interior fixed point, but it's unstable by virtue of this condition. And all those 3 fixed points are also unstable in the sense that they are invariable. If you take the fixed point with only 1, then it's invariable by N3. So a tiny bit of 3 will destabilize these fixed points, and you will flow there. And this, by this condition, proceeds in a cyclic fashion. And what we discussed is that if you start from any initial condition which is strictly in the interior of this domain with positive signs, you will cycle through and then approach this cycle here. But while doing so, the dynamics get slower and slower. And see if I plot the dynamics of N1 as a function of time. You see something that looks like a cycle, but with an increasing period or cycle length. Okay. And so what I wanted to discuss to start, what I wanted to explain today is why this happens. And can we understand this condition?
Do you know whether there is an equivalent model still in loading? In a case in which, you promote, for example, this, just variables, just the cube in 3D, with one and two and 0, you promote this to some hyperplane geometry. You see what I mean? Here, the condition is just the Ni,
yeah,
that to be positive. Do you know, for example, if you, and this is like logica Volterra, so it's do you know if I take, for example, an equivalent MacArthur still in low D, whether one can have this, like where I have sources and species, if I can get in picture for a low dimensional.
Yes.
You can.
Yeah.
Models work.
Yeah. Because essentially,
I mean, if you take, for instance, three species, three resources, you have a six-dimensional phase space. That still obeys this constraint, which is absorbing hyperplanes at each boundaries of
But
the
the
system.
absorbing hyperplanes are still like R mu, so the resource is going to zero or
Yes.
the Ni, and there is no model where this mixes. Like, I mean, you have some linear combination of the species that makes some kind of boundary where the dynamics turns very, very fast.
I would say, I guess it's possible, but I can't pinpoint you to a model right now where this would be true.
Okay.
Oh, so so let's go here and let's assume that I performed n cycles, and at that point I am going to be n1 is small. Yes, I'm here roughly after n cycles. Okay, so I'm close to n3. And n1 is small, but is small by some finite amount. So I'm going to call n1 equal u, n3 equal y minus v, and n2 is equal to vn 1 to 3. So n2 here, because I'm on the heteroclinic orbit between 1 and 3, n2 is expected to be very small here. And as we get closer to the cycle, we'll see that this guy, as n increases, after n cycles, this guy gets smaller and smaller. So that's the assumption. So v n 1 to 3, much smaller than u v, that are themselves smaller than 1. You could think about them as being order 1, 0.1. You're somewhere along this line as a small but finite distance from this. And you've done this n time. And the question is, okay, if I do the cycle one more time, what is the value of v when I fall back in the vicinity of n3? What is the value of n2? So this is at time t here. And now I'm going to say that for t prime larger than t, what I can do is just linearize the dynamics. Right? 1 minus beta 1, delta n2 dot, delta n2, 1 minus alpha 2, and delta dot minus delta 3 minus alpha 3 delta 1 minus beta 3 delta n2. So this defines the contracting direction. One minus beta is negative. This defines an expanding direction. The idea being that, okay, when the system is almost made of 3 only, then nothing prevents the growth of 2 in this cyclic fashion. So this one is an expanding phase. So after time tau, what you get is delta n2 equals tau is equal to vn 1 3 e 1 minus alpha 2 tau, and delta n1 equals tau is equal to u e 1 minus beta 1 tau. And so this one is going to grow, and now I'm wondering, so this, we assume is very small. So what I'm looking for is the time it will take to leave the vicinity of this point by having this one being, let's say, small, but order 1. So now I'm wondering when I'll be, let's say, somewhere here along this cycle. This is the new point that I'm considering. So N2 is small, but relatively of order 1. And so I can just solve for delta N2 equal to U. It's very simple, find tau, plug it here again. And at that time, I will find that delta N1 T plus tau 0, which I can call Vn. So after n cycle, when I go from 3 to 2, so the distance to this line when I go from 3 to 2, it's U Vn 1 3 divided by U times beta 1 minus 1, 1 minus alpha 2. And so if this one is very small, because this is a positive exponent, obviously this also is very small. So in terms of scaling, you get that the small number along this line is equal to the small number along this line to this power. And now you have to play the same game to complete the cycle. So back here, back here. And so what you get is that after one cycle more, so V1, 1, 3, it scales as Vn 1, 3. And so I have beta 1 minus 1, 1 minus alpha 2, times beta 2 minus 1, 1 minus alpha 3, times the cyclic combination, which is exactly the combination that was here. So the product of the Bi divided by the product of the alpha. And so if this one is larger than 1, which is the condition here, the cycle is effectively contracting. When you approach, after each cycle, you get closer to the cycle, and this is why you approach this sort of weird-looking behavior. And you see that here, because that tells you that you're going exponentially closer to the cycle. That's going to go back, exponential growth. And so if you look at the time turnout, which here I could define as the residency time in the vicinity of that point, it's logarithmic in this distance, the n. So it grows as the elapsed time, which is exactly what we have here. So the time it takes to complete the cycle grows linearly with the number of cycles that you've already made in the system.
Une question stupide. Delta N2, c'est 1 moins 1, c'est pas la même chose.
Where? Here?
Je pensais que c'était le fait que la valeur propre était plus petite.
So alpha 2 is smaller than 1. So that's by construction.
Oui, le bêta est plus grand.
Wait, so beta is greater and alpha 2 is smaller than 1. And so, okay, this could sound like some sort of a mathematical curiosity, and indeed, there are many ways to think that this kind of behavior is pathological, because, I mean, here you see that along this cycle, the population that is small gets smaller and smaller and smaller and smaller exponentially with time. So eventually, if you have a mechanism for extinction, it will die off, it will die out, and the cycle will stop. The reason why I thought interesting to introduce this problem is that in the absence of extinction mechanism, the same kind of behavior arises in large dimension, but this time generically. And you don't have to impose this sort of underlying cyclic competition. It's a generic feature of high-dimensional systems. Okay. Do you have questions?
So you know, if I take, I mean, instead of going directly to high dimension, How should I modify the condition on the product of AI and BI if I take, for example, 4 species plus?
So it's it's more complicated. I mean, there are formulas for heteroclinic cycles and their stability, but it gets quite cumbersome because essentially you see that here, by construction of the cycle with 3 species, you just have, I mean, you have this guy, which is what's happening here, but then you have one contracting direction, one expanding direction, and that's all. And when it's higher dimensional, you can get also transverse directions, which are how you grow in directions that are transverse, or how you grow or decay in directions that are transverse to the way you go around the cycle. And that makes the condition, the mathematical condition for stability, more complex. But it's been worked out. Okay.
I'm asking just because I mean when you say infinite dimension, it becomes natural. One way to see it is either you solve the model in a dimension, or you say, okay, let's take the model in the 5, 6, 7, and then let's look at what is the feasibility condition for these two apples in the coefficients A, B, A and B, and then maybe if you throw them at random, then you see that
So that is
high probability.
that has not been done. No, to my knowledge. How that probability scales with the system size. That I don't think so. Okay. So now we'd like to go to something different and then eventually bridge to this, but in some time, which is that what I'm specifically interested in this class is what happens when you have many species, and not just few. And before going back to the Lotka-Volcker model that we introduced last time in the many species setting, I wanted to discuss some earlier work by Robert May. It's May, Nature 72, paper called Will a large complex system be stable? And the question he asked was, what is the expected relationship between diversity, so here the number of species, so here you can think of diversity as the dimensionality of the system. And I'm mentioning this because the way he framed the question goes far beyond the specific case of ecological model. I mean, you can apply to a variety of systems beyond that. So what is the expected relationship between diversity and stability? Here in the sense of fixed points stability. So basically, does having more species present in an ecosystem makes it more stable in the sense of like fixed points, not fluctuating. And so the way he went on to answer that question was the following. So he said, consider an ensemble of S populations at a feasible equilibrium, and I star positive for all I. So you have an equilibrium,
And you're going to look at the linearized dynamics around that equilibrium, irrespectively of the dynamical system that led to this equilibrium. So it's like, okay, the linearized dynamics take this form, where J is the Jacobian. And what is suggested is that for a general understanding of the dynamics when S is much larger than 1, you said, okay, let's take J to be of the form minus K times the identity plus delta J. So this one would be, let's say, a self-stabilizing part. So in the ecological language, that would be competing with your conspecifics, which makes the fixed, if you're competing, that tends to make the fixed point more stable. And this encodes for species interactions. And his idea was to say, first, let's take this guy to be a random matrix. And there are two ways that are not completely equivalent in which you could argue that this is an interesting thing to do. The first one is by saying that, okay, so coming back to the ecological context, if you have several hundreds or even several thousands of species that are interacting together, there is no way, at least today, that you can that you're able to reliably infer or estimate a significant fraction of the interaction parameters. That would be, if you have S species, you need S square coefficients. There's no way you can sample that significantly. So why not take them at random? And the other way to approach this is that by taking random matrix, what you can do is to uncover or get insights for the kind of generic behavior that you can expect in large dimension. And that's also probably the right thing to do because, at least in the ecological context, but in many of those complex systems kind of studies, we don't have a proper microscopic model anyway to start with. We can propose microscopic models like the Lotka-Volterra equation based on some kind of phenomenology, but nothing tells us that this is the ground truth model. So you want to know things that are robust to changes in model parameters, but also changes in the kind of models that you're making. So this calls for an investigation of the robust properties of the model, at least when you're in high dimension. And for the sake of this discussion, obviously you can pick your favorite now random matrix ensemble. But what I'm going to do is to say that the delta J ij are IID Gaussian, zero mean, and variance sigma squared. So at large S, so this is known as the real Ginebra ensemble. And at large S, it is known that the spectrum of delta J is uniformly distributed in the disk
here we're in the complex plane. The matrix is not symmetric, so the eigenvalues are complex. It's uniformly distributed in the disk of radius sigma square root of s, where s is the size of the matrix. So the matrix is S by S. So now if you look at the spectrum of J, you will get something like this. So this would be im of lambda, real part of lambda. So this is the spectrum for J. And so here you have minus k. And here you have this circle. Filled with eigenvalues. And this circle is of size sigma square root of s. So what emerges from this picture is that the stability of the fixed point that you're considering is governed by the competition between the stabilizing effect of self-interactions here, pushing the circle towards eigenvalues with negative real parts, and the nature of the spectrum of delta J, which tends to be destabilizing as the number of species grow. And so what you get is that this fixed point is stable if k is larger than sigma square root of s, and unstable if k is smaller than sigma square root of s. And so the conclusion is that at least in those models, generically increasing the number of species does not make the community, the ecological community that you have more stable in the sense of fixed point stability. So, so yeah, maybe a couple of remarks. So, I mean, this idea, I mean, there's nothing about ecology here, just postulating some Jacobian. So this idea goes well beyond, as I was saying, ecological dynamics, for instance, to study neural networks. It's been applied also, or I mean, it's something that is coming up again and again. And obviously, this argument doesn't tell you anything about the kind of fixed point that you reach or how you reach them, nor about what happens when you go past the fixed point stability transition, because that's something about nonlinear dynamics, which is not present here. And in order to address limitations,
What we learned in S, when the number of species increase, you go towards stability.
yes, and essentially what that hides is a phase transition between two different kinds of dynamical variables as you vary this condition. So when this condition increases the threshold, you go from a fixed point to a chaotic regime. That's all.
Question about the randomness in J. Do you know? Okay, sorry, maybe not a question. That you say, okay, it's reasonable to take J to be random. Do you know if any? I mean, I guess, but if one has tried to learn the J's from the top, like, look at species upon species window, then you look at 1 point average and 2 point average, and then you try to reconstruct, assuming that there is a slot terra there, you try to reconstruct the J's in like very.
So not in very big populations. So the thing I know, which I'll discuss more at the end of this lecture, if time permits, but I can tell you we're here, if you're asking. So they had a set of experiments with, so it's about grass. We have a collection of grass species, not that many, I think it's 10. It's not crazy number. And in those experiments, they have plots where you have just one type of grass. You can look at how it grows when it's alone. and you have all the sub-samples with two, all pairwise combination of types of grass. And in theory, in the local ultra model, where you have only pairwise interaction, that's enough, because everyone coexists each time, that's enough to infer the interaction coefficient. Now you can do a sample with 8, everyone together. The first thing that they show is that the interaction coefficient that you infer from the pairwise system is consistent with what you observe in the S equal 8 coexisting system. And now you can say, okay, so you can start to play a bit of a game, and I'll come back to that later, which is to say that the species that I'm seeing, they're coexisting. So actually, there is some constraints on the interaction matrix of these species due to the fact that they are coexisting. So that's not purely, if you think about the local ultra with random interaction, that's not purely random because there has been a selection process that makes that these species are coexisting together. So this induces some additional structure into the interaction matrix, which is consistent with, what you predict from the theory and what they see in the data in terms of how the size of the coefficient depend on the population sizes or things like that is consistent. So that may be along your line the most.
So for example, bacteria, nobody looked at like
Not that I.
Specific question, but what is the center of the disk 0?
Yes, so here for delta J it's 0. And now there was this term which is just minus K identity, so that's why or the full spectrum, that's why you push by K. Yes.
Exactly. This is my question. Is you have a lot of species, but you take the same K for all of them. Is this? I understand that mathematically it's easy, but is this realistic? All the species are identical from the point of view of self-stabilization. And if they are different, then you cannot just sum.
No, I agree. But at some point you cannot avoid the fact that this guy, for generic random matrix ensemble with coefficients of order 1, the bulk spectrum will inflate with the size of the system. And so at some point you will overcome the diagonal part that you can put. And in the local ultra case, I'll come back a bit to that with variance also in the individual species parameters. So this is just for just a simple.
there are two instability mechanisms, right? So if you take the K to be random, then the stability depends also on the tail of the K.
Yes, of course.
So you could have two instability mechanisms, one for the J, the other one for the K. So this type of like GOE plus diagonal matrix, that's strategy for mathematicians. That's something that's Schnelli and so other. So organization property.
So now, what I was saying is that this is limited in scope because you just postulate some kind of linearized dynamics from the start. You don't see where it's emerging from, and you cannot explain what happens when you go past the transition. And so in order to address those questions, what we'll be looking at now is the local ultra dynamics that I introduced last time, but with many species. And so some of the relevant reference, not being exhaustive here, but that's the work by Oper and Giedrich. which is actually much older than most of the literature on this topic, but somehow it didn't pick up at the time. And then there's the much more recent work by Gage in 2017. And maybe for a more pedagogical entry, there would be the work by Tobias Gala on the archive. That's so the model I'll be considering is the following. Alpha ij and j. Okay. And what I will assume is that alpha I is larger than 0 for all I, meaning that you have you're competing with your conspecifics. And so that allows me to redefine the units of n so that alpha I is equal to 0, to 1. And now following May, we consider randomly sampled parameters. So this is a quenched randomness in the system. The parameters don't change in time. And so I'm going to set alpha ij, or I different from j, is equal to mu. So some level of average competition plus sigma square root of f z ij. So assuming that the variance, I mean, I'll tell you exactly what I'm taking for this one. But here I'm assuming that the variance of the disorder scales as 1 over square root s when s is large. This is exactly in order to get the sweet spot of this mechanism where you can cross from stable to unstable. I will take for the following, but then I'll discuss some generalizations that have been made. I will take the Zij to be 0 mean Gaussian variables with Zij, Zkl. So not all of them IID as above. Bit more complicated setting where so this is delta Ik delta JL plus gamma delta IL delta JK. So there are variance 1, and gamma is the correlation between Zij and Zji. So that way I can balance towards more symmetric or anti-symmetric matrices. Okay. So here gamma belongs to, I mean, it's larger than -1 and smaller.
And the last point is that I will take Ri is equal to R plus delta Ri divided by S with delta Ri. IID random variables. So this scaling with S will allow us to get a well-defined theory when S goes to infinity. And also the delta I have finite variance. And this is known as the weak scaling or weak interaction regime. Most of the literature take the mean mu to be of order 1 over S. Yes?
The delta or I are random variable, or are they good? Or just
Finite variance. They can be anything. And they have some distribution, some underlying distribution. So yeah, typically its mu is taken to 1 over S in the literature. But it's doesn't change much, let's say, to the physics. Or it changes little to the physics. But it's more, I mean, I prefer to take this because it will link more nicely with things that I will discuss afterwards. And by contrast, there is the strong scaling regime, which is that the variance of the interaction coefficients are for the 1, if there are 1 over S. So now for a given set of
Sorry,
yes,
the delta Ri have zero mean, at least.
yes, I mean the mean you can. Yes, you're right. I mean, if they are not zero mean, then their mean will just drop out, the same way that R will drop out. So yeah, let's say that there are zero mean, but it doesn't change. And so now, so you have a model that you can run on the computer, see what happens for a given set of initial conditions, for a given realizations of this matrix, or a given realization of this disorder. And so if you start with random IID initial conditions, the first thing that will appear or the first thing that I want to discuss is the idea of self-averaging. So if you take the empirical average of any observable of a signal trajectory, so that's a functional of the trajectory, then this, when S goes to infinity, converges or concentrates, because that's the random variable. It depends on the initial condition, the parameters of your model. But this concentrates to the mean of this observable when S goes to infinity. And this is an average over everything, over the initial conditions, over the R, and over this. And that's interesting because that tells you that collective properties quantitatively, when the dimension of the system is large, they only depend on a few now parameters.
I don't understand the notation O or whatever.
So that's an observable, a functional of the trajectory. So collective properties, they depend on sigma, mu, gamma, and the distributions of delta R, and also the initial condition or the distribution of the initial condition if you're looking at transient properties. So it just depends on a small number of parameters and this function.
But I mean, so it's supposed to be things that you could also remove the expectation on the random. This expectation on the randomness you could also remove. I mean that in the S to infinity limit, if you consider some initial condition that is taken at random, you don't average over random.
So
there is
what randomness you don't want to average?
every randomness.
But then you have this, I don't know, then you have the same thing here and here. No, what do you mean? I mean, to prove self-averaging, you need to average over something. Should I?
Sorry. Yeah.
No, maybe you meant something else. I don't know. Yeah. Okay. But I mean, I agree. Since you have convergent, I mean, concentration of this, you have concentration of this average only on the initial condition. I mean, all partial averages would also concentrate to the same value. And because now the behavior of the system just depends on a small number of parameters, that means that you can actually do a phase diagram.
So maybe I can say something.
Yeah.
I wanted to say that I mean the quantity on the left, it counts. Okay, you can write it that it's equal to the average, but you can also say that for any everything is supposed to a function that is in the S.
Yes, which is this average.
Yeah.
Which is this average. But yes, that's the statement.
Yeah, I mean, I'm just saying this because I mean, one thing that you could do is either you do numerical simulation and repeat over several cycles, or you forget and if S is sufficiently large,
Yes.
please concentrate on other deterministic functions.
But if you want to prove this numerically, you need to do several runs and see the convergence. Okay. So yes. So I was saying now you can do a phase diagram of your model, and you just have a few parameters to vary. And okay, so here I'm going to draw it when delta Ri is equal to 0 for all I. Otherwise the shape, the exact shape depends on the distribution of delta R, but the physics is not altered. So at fixed gamma, we have those two parameters. You have mu, you have sigma. Here you have 1. Here there is the value square root 2 1 plus gamma. There is a line here that separates two regions. One is a fluctuating phase. Here was a fixed point phase. And here, and I'm not going to discuss much about this, but we have monodominance. So in the fixed point phase, if you run the dynamics, you'll see something typically like that. So initially you have fluctuations, but then, I mean, as the name suggests, you converge to a fixed point. At the fixed point, some species will go extinct, and some other will. Here in this phase, so you can be more precise about what's happening. The only thing that I want to say now is that this phase is not this, in the sense that you don't control these points and population sizes keep fluctuating. And you would observe something like that. Here, that's a bit of a different regime, because when mu is larger than 1, what you can show is that fixed points with a single species, all of them are all linearly stable. And so in the end, the system just falls into one of those fixed points where you just have one surviving species. So one surviving species. And so we are far from the collective behavior of many species that we want to investigate.
Well, what is the fact? I mean, in case you have some species that vanish,
Some of them.
the others don't go to constants.
Yes.
Why wouldn't they fluctuate as? I mean, it seems there is a correlation between the fact that species disappear and no fluctuation, or no species disappear and fluctuation. On the second graph, you have no
That's true. That's true. In the second graph, we'll see that no species go extinct, actually. In the sense that fluctuations, I mean, there is a tight correlation between fluctuations and diversity. But it's a bit of a weird thing, because they don't disappear, but in the same sense as in the main neural model, none of the free species goes extinct. So, but that, I'll come back in more detail into that. That's right. Okay, so maybe maybe before moving on as to how this kind of thing can be explained, earlier I was telling you that, I mean, when you do this, and if you want to say something that is relevant for a real ecological system, you better focus on properties that are robust to changes in the parameters of the model, such as these guys, but also robust to changes in the model itself. So there has been a lot of, I mean, people have tried in a lot of ways to generalize this, the models that I was showing you before. So I'll just mention a few of these realizations. The bottom line is that most of them, when you put more ingredients into the model, you're able to ask more questions, obviously, about these new ingredients. But none of these modifications have really altered the physical picture, which is here. And here, I mean, the physical picture here is itself a translation of what May was saying earlier, with this transition between a fixed point and a fluctuating phase. So some generalizations. So instead of considering this ensemble, which are called real elliptic ensembles, there has been a generalization to broadly understood spherically symmetric ensemble. And this is by Pirey, Martinez, Pirey 2025. So more general matrix ensembles. We have heterogeneous interaction networks. So here of finite large connectivity, because here I'm taking a system in which there is multiple interactions. Everyone is interacting with everyone. We could start to relax that and say that there is an underlying graph structure of the interaction network. Start to remove some links on this graph and see what happens. So this is part PRL 2024. Consumer resource models. So I was mentioning them last time, where you model at the same time the dynamics of the population size and the dynamics of the resources that are being harvested by the populations in order to grow. These are a bit more mechanistic models than the Lotka-Volterra model, which is very phenomenological. And that's good reference for that is Blumenthal. PRL 2024. And some people have also added a low-rank structure to the interaction matrix. So what I mean by a low-rank structure is to say, okay, among these S species, I'm going to say that they have a group of S that are top predators, some mid guys and some lower guys start to put this kind of structure on top of the disorder. And so this is also Pirey plus 2025. Other generalizations have been considered. Yes.
Am I right to say that if we add, say, an anneal noise, so like our old lambda noise that we had at the very beginning of the lecture, to this model, and we add also the influx, the physics the same.
So what do you mean by, where do you want to put the noise? Because in all those models, if you want to be consistent, you have to put it in a way such that the noise respects the absorbing boundaries at n equal to 0.
It's really important that, see, in this model, is it important that somehow you're never going to reach, because you're deterministic, you're never going to reach the absorbing state?
If you put the square root noise, which leads to finite time extinctions,
Yes.
in 0 dimension, maybe you have to wait a very long time, but in 0 dimension, you always end up extinct.
If I put also the influx, so the lambda that we were
the lambda. Okay. So if you make a competition of both, I mean, it doesn't really make sense to speak about a fixed point phase in that case, right? Because then you cannot reach a fixed point. And if you put the lambda, that significantly what changes even at the deterministic level is that it significantly changes a bit the shape of the phase diagram, and it alters the physical behavior in this phase. And that I'll discuss later.
In the second generalization, what do you mean by finite large connectivity, like Arnoulx interaction? And do you know if anybody looked at cases where the JJ are Levi?
Let me think. I don't think so. I know it's something. I mean, it's something that people are doing. I don't think anyone actually did it, but I might be wrong. And so, what I want to tell you in the second part of this lecture is how one can get this phase diagram analytically by a method called dynamical mean field theory. But I think it's time for a break. So, how much time?
10 minutes.
10 minutes. Okay, we'll see you in 10 minutes.
only.
Okay, so so now what I want to tell you is I want to tell you a bit about the tools that are being used in order to derive such a phase diagram. And the main tool is what is called dynamical mean field theory. So the idea, physically, if I start from the model, this was my initial model. And what dynamical mean field theory achieves when S goes to infinity, large S, it's an exact force draining procedure where the effect of interactions, so this term, is replaced by what we will call a retarded friction bearing on the terminology in the Lagrange literature for Lagrange equations, plus the Gaussian common noise. And now, I mean, this might be a bit technical for 20 minutes, 25 minutes, but I wanted to show you, because that technique is so prevalent in the field of anything complex system related, that I wanted to show you how one can achieve this coarse graining. So to proceed, and that has nothing specific to do with dynamical mean field theory per se, but in this model, effectively, because mu here, I mean alpha, the mean is mu, this term to be of order 1 needs n to be 1 over s. There is some degree of competition, of large competition. There is a finite pool of resources. The more species you have, the more the resource is spread around the different species, the level of the species population size. So in order to get variables that remain consistently of order 1 when s goes to infinity, I'm going to introduce the rescaled relative abundances. So it's nu I. So it's ni divided to the abundance of I divided by the total biomass, total population size, times S. So this would be the relative abundance. And S here is the rescale relative abundance. So that the average over species of this guy is 1. Now, if you look at what the dynamical equations become in terms of this variable, I mean, it's a simple bookkeeping exercise to get that. And this, okay, this first, this the total population size, I'm going to call it M. So you get that d nu I dt is equal to 1 over x nu I times gamma plus delta Ri minus m 1 minus mu I. Need a tiny bit more space. So mu I dot is equal to 1 over S mu I gamma plus delta I minus m 1 minus mu I minus m sigma square root S sum over j different than I Zij. Okay. So you recover the different terms. I mean the multiplicative growth in those new variables, the contribution coming from the individual variance in the species growth rate, the self-interaction term, and the interactions with the other species, where here gamma is a Lagrange multiplier that enforces this constraint. So it's just 1 over S, sum over j, mu j, delta Rj, plus m over S, 1 minus mu, sum over j, mu j squared, plus 1 over S, sum over j, mu j, m sigma square root S, sum over k, different from j, alpha j k, mu. This is just the Lagrange multiplier enforcing u equal to 1. And lastly, there is an equation for the total population size, closing the system, which is dm dt is equal to m r minus mu m minus gamma divided by s. Okay. So as s to infinity, you can look at the different terms. I mean, you see that this guy takes the form, it's a sum of empirical averages. 1 over s of mu j squared, 1 over s mu j delta rj, 1 over s mu j times this guy. So what we will find that gamma remains 1. And now if you look at that, that means that there is a rapid convergence of m, the total biomass, to its value r divided by mu, to leading order in S. And this, on the other hand, evolves slowly on time scale 1 over S. So after rescaling, and that will lead us to the equation that will be the starting point of the DMFT. So the rescaling is the following. It's sigma is equal to 1 minus mu sigma hat. Delta r hat is equal to 1 minus mu r mu delta r hat. And t is equal to s mu 1 minus mu r tau. Once you do this rescaling, you get a simpler looking equation, which is mu I gamma plus delta r I minus mu I sigma square root S different from I Zij mu j, and gamma is equal to, as before,
Okay. Now effectively what we obtain is a closed set of equations for the dynamics of the relative population sizes. And the total population size in this language is a fast variable relaxing rapidly to the steady state value. And this is the dynamics that we want to analyze. And what I want to show you is that if you're looking at, I don't know, the average of one body observable, like the one that I was writing before, this 1 over S sum over I, O of Ni, to look at that, it's completely equivalent to look at the average of a certain stochastic process that I will identify now. So now derivation, or I'll show you the steps of the IPFT equation. So the first step so let's say that we're taking P, that's a finite number, of degrees of freedom. So for instance, nu1, nu_p, and define the generated functional as this. So I want to compute this generating function for a finite number of degrees of freedom. And so the average now is an average over the delta I, the Zi, and the initial conditions, which I'm assuming are independent. And in the Martin Pigia Rose Janssen de Dominicis, long name, formalism, this expectation value can be written as a path integral, which takes the following form. So there is still, for a given, so there is still the average over the disorder, the frozen disorder, the quenched disorder. What I'm going to write explicitly is the average over the distribution of the initial condition. So these are the initial conditions. And now, given these initial conditions, I want to enforce and consider only paths that satisfy this equation of motion. And this, I'm going to write it as path integral. And I'll explain the different terms. So this is an integral over the path nu I hat. I'll tell what nu I hat is afterwards. D gamma hat. And what do we have? So we have this guy equal 1 to P, I, and the exponential of I sum over J
mu j hat mu j dot minus mu j that's delta r j minus mu j minus c j. Times exponential of I at gamma hat gamma minus it's a long expression. Okay, so what are the different terms in this expression? This one, for instance, if I look at gamma hat, so these are functions of time. I'm integrating over all functions. And this guy is just the Fourier representation of the Dirac delta, imposing that gamma is equal to this. Now I have this guy, and this is the Fourier representation of the Dirac delta that imposes that psi j is equal to this guy, zjk nu k, similar k. This one is obviously the initial thing that I want to compute. And this one, same thing, is the Fourier representation of the Dirac delta of this equation, nu dot equal nu j times blah, 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 which is the equation of motion. And now I'm conditioning this, our path condition on starting at some initial condition nu I 0. And this is the average over the initial condition with with this initial distribution, which is P IID for the different degrees of freedom. And closing brackets for the expectation value. Now what I want to do is to here I have to take the expectation value with respect to the random parameters delta r and z, and I want to start by taking the expectation value with respect to z. And this form is quite convenient because z appears here. Z is a Gaussian variable. It's a set of Gaussian variables, and we have to take the exponential of, the average of the exponential, and that we know how to do for Gaussian variables. So what we have to compute once we push forward the average, the expectation value here is this. So it's the exponential of the expectation value of the square. So you get j from j, sum over L, m from L, z, j, k, z, L, m. Now you get a double time integral, d to 1, d to 2, psi j to 1, mu j to 1, psi L to 2, mu m to 2. And this one selects only pairs LM, which are equal to JK or KJ. That's because of the initial, of the ensemble that we chose. The variables are independent, except when we permute the indices. So then we have one contribution
from L equal J, K equal N. And one contribution from the L equal K, M equal J. And then there is times exponential, and there is a small part that remains, but that is subleading in S. I'm not writing it. So now what's interesting is that what features in the remnants of the average over the interaction matrix coefficient are these two order, effectively time-dependent order parameters. So I'm going to write C to 1 to 2 is equal to 1 over S sum over K mu K to 1 mu K 2, and R to 1 to 2 is equal to 1 over S sum over K mu K to 1 psi hat K. And you might see here from this expression that once I will introduce same thing, Fourier representation of these identities. And once you do that, so here, if you forget about this term, here the different J's are effectively non-interacting, right? Sum over J, there is no new K here. Sum over J, there is no new K here. Here, there is a coupling. Okay? This is the interaction part. Once you average over, this is what becomes of the interaction, but it groups into this sum times this sum. And so if I represent this by this order parameter by the Fourier representation, effectively I've completely decoupled my different degrees of freedom. And eventually what you will get is this, after a bit of rewriting, is that you have the expectation. And now the only expectation value that remains to be taken is with respect to the delta r's of, so there is d gamma hat, and then there is dc hat for this delta constraint, dr hat, exponential of is times gamma plus q hat q plus r hat r times the product I equal 1 to p, and I'll explain those different terms, where this expectation value is, so let's say that I have an observable O defined by. So here you see the different terms, the different I factorizes, decoupled, and this is this. What remains here is the measure once you decouple them, and it's d nu 0, d nu 0, nu 0, d nu hat, d psi hat, times this observable, or any observable, exponential of p nu hat times nu dot, so the equation of motion, and now that's interesting because if you look at this, this is enforcing the equation of motion that we had before. And now this equation, this set of equation, tells you that psi is equal to an average term times the fluctuating part, which is Gaussian. That's exactly what you would get for the representation of the Gaussian noise. And so this measure is associated to a Gaussian stochastic process. I mean, the stochastic process with Gaussian noise, rather, which is nu dot is equal to nu gamma minus nu plus delta r plus sigma and where psi is a Gaussian noise. Psi tau prime is equal to C tau prime. So now I didn't tell you what are R, R hat, and C, because there are still, in this formula which is here, there are still integration variables. So for each value of R, R hat, C, etc., there is a corresponding stochastic process over which you have to average. The key part is that there is a factor S here. This one is also a product of S minus P term, so of order S. So effectively, for this variable, there is an underlying large deviation process in the variable S, which is going to select a saddle point solution, which will then tell you what is the value of R, R hat, and C that you have to put in this equation to compute averages in statistics. And this is achieved.
delta R. Because now, if I take this formula for Zj, and I distribute the average over the delta R's, because now, I mean, these are independent, all the delta R's, so I can do that. And so you have an integral over those fields. Here there is a functional f, which is the exponential weight, all of them. And then I am left with the product I to p of e mu I j I minus L, where f gamma gamma hat e hat r hat is equal to, and there is an s here. Sorry, so here it's product I to p, but there is an expectation value with respect to delta r. So it's I gamma gamma hat plus q hat plus r hat, that was written above, plus the exponential plus the logarithm of the average of e minus L delta r, plus some subleading correction. And this guy comes from this guy, where I can take the average, and then all of these are the same, and I can raise it in the exponential by taking the log. And so now, what is going to dictate the choice of gamma, gamma hat, c, c hat, r hat is the Laplace approximation of the integral with this. And maybe just a comment, what we will find in the end, once we do this, that at the saddle point, the fields gamma hat and c hat are equal to 0, which implies that L is equal to 0. Sorry, I don't think I told you what L was. Sorry. So there is this L here, which I'm using here, and L.
Maybe also Q, I don't know what it is.
Sorry? Q.
Capital Q.
Here? Yeah, it's because it's a C. Sorry.
mu delta r minus mu squared sigma hat psi nu minus I q hat mu. So if gamma hat and q hat are equal to 0, L is equal to 0, and what that leaves is that the z of j is just equal to this. The product of the exploitation value of I mu I d I delta r. So what this equation tells you effectively is that if you want to compute any observable for a finite number of degrees of freedom, it's as if these different degrees of freedom behave independently. Like here, the generating functional is just a factor of individual generating functionals, evolve independently according to this stochastic process, with the proper value of r a hat and q and c, sorry, which are the result of this saddle point evolution. Yes.
So essentially, you were able to do this saddle point over just the C, R, and gamma without considering if you want the dynamics, just because you.
So you have the dynamics here. Like this is the part that, I mean, the dynamics is effectively what.
My question is on the, you see, at the very top you have some product over P, or I from 1 to P.
Yes.
That term is subleading with respect to the order.
It's order 1.
And so this is the reason why you're neglecting it for the saddle point.
Exactly.
This is kind of the way this machinery works. So if you take P to be S, that's of order S.
If P is order S, that doesn't. That this independent, the statement of independence is valid only if you consider, I don't know, 2. If you look at correlation function of 2 degrees of freedom, you will see that the decay as the system size goes to infinity, decay to 0. So for this kind of observables, it doesn't matter. However, if you start combining a lot of things, even if that by pair by pair the correlation is small, you could still get effects in the end of these correlations. If you look at collective observables, like high-dimensional observables. So yes, the important thing is that here P is of order 1, or subleadingness.
No, in the definition of L, the last term is C hat.
Yeah. Sorry. Oh. And the last thing that we have to do is to look at the saddle point equations. Which number was I? So if I differentiate this guy first with respect to gamma hat, here I get gamma. And on the other side, I get contribution from this guy. So I have 1 over the average of E minus lambda delta R from the log. And then when you look at how this average varies when you differentiate with respect to gamma hat, we get this. Because I remind you that L was gamma hat and the integral of gamma hat times this plus other terms. So when you differentiate with respect to gamma hat, this is everything that's right. And then you can keep going. So Q up to this L, E minus L, is the correlation function nu, which is, I mean, that's what it represented initially, right? That's the constraint that we impose with the delta function. And R is the correlation function of nu times the noise, psi hat. And now you can differentiate using similar equation when you differentiate with respect to gamma C. C. We have a problem with the C's. With respect to gamma C and R, and what we get is gamma hat is equal to the average of nu hat nu, A minus L, IC hat is 1 of the average of psi hat, A minus L, and R hat, so 1 to 2, you will find that it's gamma divided by 2I R to 2 to 1. The interesting thing is that now we have these equations. They are not very nicely looking. But by normalization, what we have is that nu hat nu delta R is equal to psi hat delta R, and this is equal to 0. No, nu hat nu. That's because of the multiplicative structure of the process. I'll show you. It doesn't play the same role as psi hat. Those are equal times.
Equal time.
Yeah, those are equal times. I mean, this one is equal time, and this one is any time. Yeah. And and in fact, what you can show to see where this is coming from, this normalization condition. Which is standard in the path integral representation of stochastic process that has not so much to do with dynamical mean-field theory per se, is that if you have for any observable O and field H of t, so if you look at this expectation value, nu hat nu H of t, or H of tau, delta R. This is equal to O to the average of delta R, where now this measure, it just amounts to putting a perturbing field H of tau. Nu dot is equal to nu gamma plus HT minus nu plus delta R minus sigma psi plus sigma beta prime, and the same kernel as before, R tau to prime plus R hat to prime tau mu to prime and psi is equal to C. Like putting this expectation value, adding this, it's completely equivalent to putting the perturbing field. And so if you say O is equal to 1 now, what you get is this for any field H by normalization. And so if you take the first derivative with respect to H, you get this expectation value on the left hand side and you get 0 on the right hand side. That being proven, and the same goes on for this. I mean, you have similar arguments. It's just you can define the same generating function and you get something similar. So here, what you get from this is that gamma hat is equal to 0 and C hat is equal to 0. These are solutions. Indeed, if I put gamma hat C hat is equal to 0, then L is equal to 0. I have 1 by normalization in the denominator. And now I have nu hat nu, 0, psi hat psi, 0. So this is the saddle point solution that you're looking for. And what remains of this guy now is just the average of nu to 1, nu to 2. And this guy is the average of psi of nu to 1 psi. And so that will allow me to conclude with the DMFT that essentially now we found the stochastic process that we're aiming for. Which is that, so let's say, therefore, the dynamics of population sizes behave as independent realizations of the stochastic process. And I'll write the final result, and I'll stop here for today. So nu hat is equal to nu gamma minus nu plus delta r minus sigma psi minus sigma hat square gamma beta prime r tilde delta prime nu to prime plus h. So this is just so I have this Gaussian noise. So this guy is Gaussian, 0 mean. It has to be equal to, I don't know its correlation, but it has to be equal, its correlation function, to the correlation function of nu. That's what's here, when you put it inside. So this has to be self-consistent. And this guy, so R, I was telling you, is the correlation of nu with the noise. And for the same reason that what I was showing you before, to show that this is equal to 0, this correlation function is equivalent to a response function when you add a perturbation h, here h of tau. So to give it a more physical meaning, I've written it this way. So you have the kernel
R(P2 prime) is equal to the average of delta H2 prime nu delta R. So if I put a small peak here at tau prime, how does the mean at tau changes? And gamma, as before, is the Lagrange multiplier, so that the average of nu is equal to 1. And this is at h equal to 0, so it's linear response. And so this is the final outcome of the MFT. It tells you exactly, I mean, this is the exact coarse graining procedure that I was telling you about, where this comes from the single species dynamics. And all of this, meaning the noise, plus the retarded friction, the retarded kernel, is the outcome of interactions. And I will stop here for today, and then now that we have derived this equation, we'll see next time what they tell us in terms of behavior of the dynamics. Thank you for your attention.
When the notes will be available?
Yes. When?
Well, I mean, could we make a scan and distribute to people?
Yeah, of course. That's what I was gonna say. I have handwritten notes on this, a tiny bit more detailed that I'm happy to pass, and soon there will be proper typed notes that I can't commit on when. So.
Okay.
So yes, I mean we can do that definitely.
So those who have not already done, contact me. I mean, I need the email. That's the point. And there are physical questions. Just to summarize, I'm confused. First, you said it is exact, then you said it is you discharge some subleading terms.
Yeah, so it becomes exact in S to infinity. That's the result S to infinity. That's the exactness where it lies.
Okay.
Like all of the subleading terms that I didn't write are order 1 over S.
Okay.
Compared to what we're considering here.
I just want to be, the noise was here at the beginning, or it appears?
No, the noise appears from the result of interactions. The same way that when we have a colloid in water, we put this like Gaussian white noise to account for interactions with the solvent molecules. The big difference here, so there are two different. I mean, if you do Langevin, and maybe it's an interesting thing to say, for a colloid in water, there is a friction, and there is a noise. And we use this argument of separation of time scale to say that both the friction of the noise can be taken as instantaneous. So you have Gaussian white noise, and the friction becomes typically instantaneous. And just, I mean, this is just the derivative of the delta function. And that argument works because there is clearly a separation of scale between the colloidal particle that you're looking at and the solvent molecules. Here it's a bit the same argument in the sense that we replace the effect of the interactions with all the other degrees of freedom by a noise and a kernel such as this. But now there is no intrinsic difference between the degrees of freedom that have been coarse-grained out and the degree of freedom that you're singling out. So you can't make this separation of time scale hypothesis. And in fact, the kernels that you find here have to be self-consistently related to the statistics of nu. So that indeed the interactions come from guys that are equivalent to the one that you're looking at. That's a bit the.
So it's not instantaneous anymore. I mean, you can...
Yeah, no, it's like a. I mean, you get time delays, and it's non-local in time. That's what Henri was saying last time. That once you have interaction, indeed, they propagate in the network, and you get non-locality.
Other question? So online there is a problem. So thank you.
Okay.